Cordial greeting to all people. My name is Jonathan Chirvisa. The subject of my presentation is the key aspects on the transition to a new electric mobility paradigm, impact on electric vehicles, servicing, maintenance, and repairing. I'm going to talk about many aspects of electric vehicles maintenance with safety systems, braking systems, coolant systems, battery, wheels, and end-of-cycle life electric vehicles. The principal motivation was the electric mobility is one way to promote the decarbonization of the transport system as an alternative to conventional combustion engine technologies and fuel. The recent sales increase of electric vehicles at the global scale is a strong indicator of transition that is taking towards a new electric mobility transportation shift. Nonetheless, several challenges have yet to be overcome as EV technologies, higher autonomies, lower battery charging times. Current autonomy companies and service providers have yet to fully adapt to the challenges and demands related to EV maintenance and repair. And of the world to describe and analyze the challenges of automotive maintenance service due to the introduction of electric vehicles technology and how service providers will assume this change. We first challenge have the safety. EVs require additional safety precautions to protect the service technician. Vehicles design and workshop procedures but must adapt to meet these heightened safety needs. Safety by design. Integrating safety mechanics into design of the high voltage wiring and systems. For example, high voltage interlock loop, short circuit monitoring, potential equalization lines. Other challenge is the workshop safety. High voltage vehicles need to be separated into dedicated bays for diagnostics and service. Proper signage and physical barriers such as fence we can observe in this image and these are necessary to ensure that employees know which vehicles have high voltage components and thus which service bays to avoid. Signage can help communicate the state of a vehicle to all technicians clearly and concisely. Personal safety. High voltage technician needs special insulated tools to protect themselves from electric currents. Also, they need personal protective equipment. For example, gloves, eye protection, masks, and coveralls. Furthermore, special containment is required for safe storage and ship critical batteries. Training. Training for high voltage or high voltage system in electric vehicles is crucial due to the unique requirements and precautions of the system in a service environment. A service environment encompasses many different people with the different roles that work in and around vehicles under service. Therefore, different levels of training are appropriate for different employees. The first level of training focuses on awareness. The second level, safe working, level is high voltage technician training. The third level, advanced. Technician needs to undergo advanced training to act as the high voltage expert in a service location, build facility, or dealership. Batteries, life cycle batteries. Electric vehicle batteries typically reach their end of life for used vehicles after about 8 to 10 years, or 150,000 or 160,000 kilometers, when the capacity is below 80%. However, there can be opportunities for reuse the batteries and recycle the batteries. end-of-life vehicles in terms of process of treatment of an EV at the end of its useful life. It begins with the cancellation of vehicle registration. Then it is transferred or transportation to an authorized dismantling center, where it is dismantled. At this point, the components that are dangerous to a health are collected, such as batteries and other components. Then the other materials are recollected for secondary use. The non-recycled components are crushed, and finally the ferrous materials are separated from the non-ferrous materials. Traction system. The energy consumption of battery-selected vehicles is strongly correlated with vehicle size and weight, as is the case for ignition combustion engine vehicles. An analysis of weight of the same vehicle models, for example, Opel Corsa, Kia Soul, Mini Cooper, and Peugeot, was carried out but with a different energy supply. Therefore, the first is an EV electric vehicles and the second is an internal combustion engine vehicles, where we obtain an average difference of 428 kilograms. In percentage is a 35.3% increase in vehicle weight. It's a difference of the weight the electric vehicles in relation with the internal combustion engine. Driving energy consumption varies across different electric vehicle sizes, between 15 and 21 kilowatts hour per 100 kilometers for mini and luxury cars, respectively. Maintenance costs electric vehicles versus internal combustion engine vehicles. Compared to an internal combustion engine motor, the electromotor of an electric vehicle has few moving components, and the driving train of an electric vehicle contains no gearbox, transmission, and other moving components. Regular internal combustion engine car maintenance, such as the replacement of oil and filters, is not necessary in an electric vehicle. The necessary maintenance of electric vehicles can be reduced to once per 40,000 kilometers, with a yearly driving distance of 16,500 kilometers. The maintenance costs of EV are expected to be 800 euros, and the maintenance costs of the internal combustion engine are expected to be 444 euros. A year or is at 12 cents per kilometer. Comparison of in-use well-to-wheel emission per kilometer for a range of passenger car drivetrains. Battery electric vehicles have superior energy efficiency in use relative to internal combustion engine vehicles. Battery electric vehicles can convert 70 to 90% of the energy stored in the battery into movement. The theoretical peak efficiency of internal combustion engine vehicles is only 40%. Comparation electric vehicles versus internal combustion engine maintenance. In this table, we can observe a relationship between the maintenance times of electric vehicles and internal combustion engine vehicles. The two models are Tesla Model S and Porsche 911. In the table, the times in kilometers and years of the main maintenance are observed. We also can observe that the period to carry out the maintenance of the electric vehicle is higher. For example, the change of coolant is replaced for 15 years. In this case, in internal combustion engine vehicle is replaced for 4 years. And the maintenance activities are less compared to an internal combustion engine. For this case, the electric vehicles don't have spark plugs, oil transmission, and engine oil. Not is necessary change. In this table, we can see an annual relationship of maintenance costs between two electric cars, Tesla Model S, BMW IA. We compare these two models with internal combustion engine vehicles, Cadillac CTS, Chevrolet Corvette, Porsche 911, and Mercedes-Benz E350. And where the maintenance cost of Tesla Model S is much less than the maintenance cost of Cadillac CTS, Chevrolet Corvette, and Mercedes-Benz. And finally, BMW IA model, it can be compared with the Porsche 911, but two are luxury cars, where the cost of maintenance of BMW IA is more or less. Conclusions. After sales service and vehicles maintenance will only become more critical as vehicles become more electrified and autonomous. These vehicles technologies create new challenges and concerns for service technicians in the repair and maintenance of EVs. With the help of advanced engineering solutions in critical systems, automotive companies can help dealerships and workshops with the necessary tools to overcome the challenges of the maintenance on electric vehicles, ensuring the safe and efficient operation of electric vehicles. Thanks.